Teams link that have been shared at the chat room. Thank you.
No.
Excellencies, Honorable, distinguished guests, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Peace be upon you. Bismillahirrahmanirrahim. It is with great honor. My name is Ali Maulidia. I'm your Master of Ceremony for today's visiting lecture. Good morning, and we are greatly honored and pleased to welcome you most cordially, Professor Dr. Hendrik Heijnis from Australian Nuclear Science and Technology Organizations, Australia, the Excellencies, Dean of Faculty of Science and Mathematics, Diponegoro University, Professor Dr. Widowati SSC MSE, Honorable Vice Dean for Academic and Student Affairs of FSM Undip, Vice Dean for Resources of FSM Undip, the Head of Biology Department of FSM Undip, the Head of the International Office of FSM Undip, Professor Dr. Triratnaningsi MAPPSC, one of Professor in Biology Department. All the participants include student and lecturer of today's visiting lecture. The visiting lecture at the Faculty of Science and Mathematics, Diponegoro University, has been held annually as scientific and scholarly meeting to invite the scientists from all over the world. The objective of this visiting lecture are to facilitate brainstorming and state-of-the-art information in the field of science and mathematics, enhance and strengthen international collaboration. Honorable students, ladies and gentlemen, now We would like to kindly invite the Excellencies, Dean of Faculty of Science and Mathematics, Diponegoro University, to deliberate opening remark. Kindly proceed to open cam. Please kindly proceed, Professor Dr. Widowati, SSC, MSc. Thank you.
Okay, thank you very much for Master of Ceremony, Mrs. Ali Maulidia. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good morning, everybody. Excellency, Professor Dr. Hendrik from Australian Nuclear for Science and Technology Organization, Australia. Excellency, Farifin PhD, as a Vice Dean for Academic and Student Affairs of the Faculty of Science and Mathematics, Diponegoro University. Professor Dr. Kusoro Adi as a Vice Dean for Human Resources. Honorable Professor Dr. Tri Retnaningsih Suprabawati. Panji Priyadarsha, PhD, as the Head of International Office, Faculty of Science and Mathematics, and also as a moderator. Dear lecturer and all participants, it is my great pleasure to cordially welcome you to the Faculty of Science and Mathematics program visiting Professor events. First of all, let us thank Allah Subhanahu wa Ta'ala, the most gracious and merciful God, because with His permission today, we can gather here to join together for virtual visiting Professor Evans. My sincere gratitude, especially to Professor Hanks, who will be today's speaker, and to all participants for their great contribution in promoting sciences and technology for Diponegoro University Academia. In addition, for today's lecture, the topic of the material is Cathment Management, new tool for managing combining sediment archive and high-resolution weather observations. It is an hour for us to get a direct lecture from Professor Dr. Hendrik Heijnis. Ladies and gentlemen, as we know that the vision of the Faculty of Science and Mathematics is to become an excellent research faculty with international reputation in the fields of science and mathematics, as well as the development of its application. This event strongly supports our mission to prepare the students who have excellence in the fields of science, also to produce competitive graduates at the national and international levels. I hope this visiting Professor Evans can inspire many scientists to improve their research and open broader international collaboration between Faculty of Science and Mathematics, Diponegoro University, and Australian Nuclear for Science and Technology Organization, Australia. Last but not least, by the grace of God Almighty and consent of all participants, on behalf of Faculty of Science and Mathematics, I am, as the Dean, hereby announce that online visiting Professor Evans with the topic Cathment Management, new tool for managing combining sediment archive and high resolution weather observation is open. I encourage all participants to participate actively in the interesting discussion. Hopefully, what we are doing today is useful for our progress in the future. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Continuing to the next agenda. Before we start our main agenda, previously we would like to introduce you the moderator of today's visiting lecture is Panji Triadiaksa, SSE MSc PhD. He is a lecturer from Physics Department, Faculty of Science and Mathematics, Diponegoro University. Please kindly proceed to officiate the presentation. Thank you.
Thank you very much. Thank you very much, Ms. Ali, for the introduction. And ladies and gentlemen, before we start the presentations of Professor Heijnis, we would like to give short introductions about Professor Hen. So the speaker for today's presentation is Professor Dr. Hendrik Heijnis from Australian Nuclear for Science and Technology Organizations. And the topic of today's event is catchment management as a new tools for managers combining sediments archive and high-resolution weather observation. A short introduction about Professor Hendrik is Dr. Hendrik is an environmental geologist with over 40 years of experience, educated in the Netherlands in physics, geography, quaternary geology, and applied physics, and he immigrated to Australia in 1993. Dr. Hendrik took up a post at the Australian Nuclear Science and Technology, an organization as a leader in applications of nuclear technique in environmental science. He becomes the head of the environment department in 2016, a position he held until his retirement in 2021. He is an adjunct professor at the Sekolah Pasca Sarjana Undip and has an adjunct position also at the University of Technology Australia and the Australia National University. In 2010, he was a visiting professor at the Royal Netherlands Academy of Science and the Arts, and he also a position of a leader climate project with the Forum for Nuclear Science Cooperations in Asia and with the International Atomic Energy Agency. So it's quite prestigious positions. And to make the introduction short, so without further ado, I would like to introduce Professor Hein to all the audience. Professor Hein, good morning. And is the time is.
Thank you very much. Share my screen. You can see my screen? Yep. Okay. Well, thank you very much, Mr. Moderator, and also the Dean of the Faculty of Science and Mathematics here at Undip for allowing me to share some of my experience today with this presentation. Of course, this is not the first time I have shared some of my expertise here at Undip. This is actually my fourth time as visitor to Undip, and I remember maybe 8 years ago was the first time I did a Studium Generale for the faculty here, and ever since I felt really welcome in Semarang, and I am happy to be back as an adjunct professor. Now that I'm retired, I have more time, less management, and more time to interact with students and to share some of my experience of my career. Today, I would like to share some of my experience when I worked briefly in the middle of my career for the Sydney Catchment Authority, which manages the drinking water for about 5 million people in Australia, which is 1/5 of the whole population of Australia lives in Sydney. And they all depend on good quality and also good quantity drinking water. And during my research since 1998, I've spent a lot of time looking into the issues of catchment management and how can I help with my expertise in geography, in applied nuclear techniques to help the managers to better manage the catchment and the availability of good drinking water. And in 1998, we had a drinking water crisis in Sydney. This was less than 2 years before we were hosting the International Olympics in Sydney. And it was not good advertisement for Sydney that we had to boil our drinking water for about 4 minutes to make it safe for drinking. In the drinking water, at the time, there were some microorganisms that are toxic to humans. They found them in the drinking water reservoir, which holds about 85% of all the drinking water for Sydney. So that was a bit of a crisis. And at the time, I was already working on sediment archives and how we can learn from them about the history of the catchment. And I went to them and said, maybe we can help reconstructing the history of your catchment to see if these blooms of the algae and the microorganisms that cause the drinking water to be of very bad quality, maybe we can learn something from the past. And we got a contract to do research, and 6 years later I worked for them. As you can see in my title, I was the program manager for climate variability and extreme events. And climate variability is, especially in Sydney and in the east coast of Australia, is driven by the El Nino La Nina cycle, but also by the Indian Ocean dipole, which is another driver, especially of rainfall or the lack of rainfall. And of course, the extreme events come in when these cycles combine, and then we get excessive rain from the Indian Ocean side, from the west, but also from the east, from the La Nina cycle. And most recently this year, in the first 3 months during our La Nina cycle, we had more rain than we normally get in 1 year. And that has caused extreme flooding and economic loss for a lot of people, especially farmers whose business were inundated by floodwater, and also the inability of people from Western Sydney to travel to work. So a lot of people were stuck at home because roads and bridges were all flooded, and that has a huge economic loss. The good news this year for Sydney was that it did not affect the water quality. Of course, the water quantity went up to 100%. So we are 100% sure that we have enough drinking water for the next 5 years now. But the water quality, as it was in 1998, when we also had a very big rain event, an extreme rain event with up to 400 or 500 millimeters in a few days. That didn't happen this year. So we have learned from that experience of more than 20 years ago now, and but we can still learn more. So that's why we have this presentation today, and hope you enjoyed the ride, and also hope you can pick out something that you might use for your own studies in the future. So the title here, Climate and Climate Change Research at the City Catchment Authority. We're looking at past changes and variability to better understand the impact of future changes. Because when we looked at the variability in climate and especially in rainfall, we know that it is very difficult to manage already in Sydney or in the whole of Australia, really, because our climate is very variable. The climate, for example, in Indonesia is a little bit less variable because you have a wet season and a dry season. And during the wet season, of course, you can always count on some rain, maybe not the average. It could be a little bit below average. But in Australia, with the variability, as I said, from the Indian Ocean and from the Pacific Ocean, in particular, the La Nina, El Nino cycle, the variability in rainfall can be very dramatic. We can have 300% to 400% more rainfall in 1 year, but we can also have lack of rainfall for a couple of years in a row, which of course has also disastrous potential impacts on human activities and society. So that's why we started looking into this when I took up that job. And the first thing that I noticed that not every scientist is a physical scientist, so they don't know exactly what weather and climate, how we define that, especially when it comes to climate. So weather and climate are, of course, two very different things. And here is just an overview of our main water reservoir. In red, you can see the inflow into the catchment, and in blue at the bottom, you can see the rain in millimeters per year. And sorry, the red is the rain and the blue is the inflow. And you can see that this is what a variable climate looks like. In these 100 years of rainfall history, you can see that there is a period, especially here in the middle, where we have very high rainfall years and also very dry ones. But in general, this whole period between 1945 and 1965, 1960, there was a high rainfall period. And as you can see here at the tail end, the early 2000s is very low rainfall and also very low inflow. And this is when we had the last peak here was our drinking water crisis. And then, of course, that was a water quality crisis. And then following that from 1998 onwards, all the way to 2010, we had a water quantity crisis in Sydney. So we went from not having safe drinking water to almost having no drinking water because the dam level went from 1998 100% to about 30% only in 2006-07. Now, this period here, going back to the 1950s, 60s, of course, we know that from the meteorological observations that we have from our Bureau of Meteorology. And this was a specifically good period for building the dam. So the dam was actually built between 1950 and 1960. And of course, while they were building the dam, it was already filling up quickly. So when it was finished, it was almost full 100%. And then we had a lot of drinking water for these low rainfall years. But as you can see, the observations only go back to 1910. So what we don't know is that these periods of wet conditions, high rainfall conditions, is that something normal, or does it occur every 20 years, 30 years, 100 years? And also the very dry conditions, does that actually occur with the same regularity of the La Nina El Nino cycle, which is a few years, or is there a different mechanism where it occurs on longer timescales. So this is where we came in by looking at archives of past climate to learn more of the last few hundred years of the history of this particular catchment. Now, this catchment, I must say, is huge. The rain that falls in an area all the way to our capital, Canberra, which is some 250 kilometers away, and even further south on the coast. And the coast has the highest rainfall in our state, in New South Wales, in Australia. And of course, that all flows into this major catchment. Now, this is a little bit more detail on how we can look at rainfall. Now, this is a daily rainfall record of the period that I was working there. And you can see a lot of periods, there is hardly any rain. I mean, 10 millimeters of rain is nothing. But then, of course, we get these high downpours here, a period in 2007, where we had a few days with high rainfall. But we need this high rainfall to persist for at least a week to result into the rivers and the creeks flowing water into the dam. So this high rainfall might be nice, but it doesn't necessarily mean that it is filling up the dam. You really need consistent rain over a longer period to make it flow into the dam. This period here in 2005 had a relatively few more days of rain with moderate rain, and that actually resulted in more inflow into the dam than these high peaks here. Now, the climate science is important to understand what you're trying to achieve by looking into the past, what we want to study, and how we can use that in modeling future climate change. Now, so I'm going to discuss briefly climate variability, the weather forecasting, and climate change. So, climate is what you expect, weather is what you get. So the climate is basically about long-term records, trends, and averages. So when the Bureau of Meteorology in Australia and also around the world, the World Meteorological Organization, defines climate as the average conditions in temperature, rainfall, humidity over a 30-year period. So, and that is then averaged, of course, and then if within that data set, you can see if there's a trend away from the average. So if the tail end of your 30 years, so at the moment it is 2022, so the climate now is defined anywhere between 1992 and 2022. So within the, statistically in that data set, if you look at all the rainfall and there is a trend upwards or downwards, then you can actually say, maybe my climate is changing. But also the climate definition is shifting every year. So you really have to look at climate in blocks of, say, 10 years, so from the 1960s throughout to 2022, to see if there is a trend in climate change. Of course, the weather is the day-to-day experience, and this is where it gets confusing because the press and the television often gets really confused, and they say, well, that talk about climate change is yesterday, or in the Northern Hemisphere, where I am from, the Netherlands, the people in the newspaper might say, well, global climate is maybe warming up, but yesterday it was very cold. And that, of course, is the weather. So the weather is the watch that you're wearing and climate is the calendar. So they're two different things. Of course, the weather long-term defines the climate, but what weather is not the climate definition per se. And this is very important, as there's a lot of confusion in the especially online, but also in the newspapers and on television about these definitions. So that's why I wanted to clear it up right from the start. Now, this is a map for Australia. As you can see at the bottom, it says this covers the period from 1900 to 1999. So that's 100-year average conditions of the seasonal rainfall in Australia. And in red here is where I live. Sydney is right there to the top right hand of the circle. And you can see the driest parts of the continent are right in the middle. That is where the deserts are. Very low rainfall, and it's you can see from the coloring that there is a trend towards summer rainfall. The opposite of that is Perth in the west, where they rely on winter rainfall. And lucky for Sydney, we are in a region where we have uniform rainfall. Now, what does that mean? Here you can see the green is more than 800 millimeters per year, and which is the area from Sydney. And the catchment that I was talking about, it forms this green bit here in the lower part of the circle. So most of it is in the area which we actually say, on average, there will be more than 800 millimeters per year of rain. Now, this is the average, as I said, from 1900 to 1999. Now, earlier this year, as I said in my introduction, we already had 800 millimeters in the first 2-3 months of the year. So this year is a very wet year for us. It's not anywhere near the average. I think in the end towards the end of the year, we probably end up with nearly 2,000 millimeters of rain, which of course is more like the north. This is the northern part of Australia as a very tropical climate. It's monsoon driven, and it has more or less the same climate as large parts of Indonesia. So as you can see, it has a summer dominant, the wet season, and it has more than 1,200 millimeters. And parts of the northeast coast here in Queensland near Cairns, they actually have more than 2,000 millimeters on average per year. But that is the average. So what does that mean? Here in Sydney, for example, we have had years where we had less than 200 millimeters for the year. And that makes it actually on par with the very dry and arid center of the continent with only 200 millimeters for the year. But as I said, an average doesn't really mean everything, a lot, but it tells you a little bit about how you can plan long-term for your water resources. Now, this is the annual rainfall. So we're now focusing in on Sydney and the catchment. So you can see on the coast, we have the highest possible rainfall, more than 1,000 millimeters average annual rainfall. And it actually goes down to the west. And then we have a mountain range here called the Blue Mountains. And there, because of the effect of the mountains on rainfall, there's high rainfall again. But the rest of the state, you can see it just goes down, down, down. And the west of the state is very arid. And this central part is semi-arid. We only do agriculture there because of irrigation from major rivers. All the rivers from this east coast mountain range, a lot of them flow in a westerly direction and form the biggest river basin, the Murray-Darling Basin in Australia. And it's used for, a lot of that water is used for irrigation. But if you halve in a given year, if the rainfall is only half, that means the flow of the rivers will be not half, but will be probably around 20%. So only half the rainfall here in the eastern part of the country on the coast will actually have a big effect on the irrigation abilities of the farmers inland, because that is, the flow is reduced by 20%, or the flow will be reduced to 20%. Now, this is what we always thought was the main driver of our climate. And these are the average El Nino, La Nina values. And you can see in blue will be the La Nina cycle. And in red is the El Nino dry cycle. So as I showed earlier, this is for the whole of Australia. So that period in Sydney from 1945 to 1960 is here, but you can see there are some peaks, but there are also short periods of El Nino dry periods. But if you look to the right here, the El Nino dry periods are actually longer here than this part here. There's an El Nino drought period here, but they seem to be more frequent towards the right of this diagram. And if that is a trend driven by global climate change, then that is a worry, because we are just learning to manage this system here with short periods of dry and then short periods of wet. But now we have to, as you can see towards the end here, very short periods, sometimes only 1 year of wet, followed by many years of dry. And that is what we want to manage, but we have to learn from the past to see if we can improve the management. So this is very simple graphic about La Nina, El Nino. So this is the surface layer of the Pacific Ocean, and it's actually measured the air pressure in the Eastern Pacific on the South American coast with the pressure near Darwin in Australia. And if the pressure is high here and low here, then of course you get strong winds over the surface of the Pacific Ocean, and it warms up, and then most of the rain during a La Nina cycle will fall in the Western Pacific, which is of course not only Australia, but also New Zealand and Papua. And in the opposite, when there is a weak signal in the air pressure between the east and the west, then of course that rain will either fall in the Central Pacific or in the Eastern Pacific. You can see it at the moment in the news. If you follow the international news, you will see that we had flooding quite a bit in Australia. But if you then look at the United States, especially California, and also some places in South America, they have extreme dry conditions and a lot of fires caused by natural causes most of the time. But there's a lot of fire going on and caused by this intense dry period. And they're also, their water reservoirs are rapidly running out of drinking water, suitable drinking water. As soon as the water levels go down, then it's not only a water quantity problem, but because of the low levels and the concentration of and the algae, but also the pollutants, they are more concentrated. So it also becomes a water quality problem. And even further afield, the very high temperatures in Europe at the moment, which are not related directly to this cycle in our part of the world, but they are also experiencing very high temperatures and very low rainfall. And it has very big economic and societal impacts in Northwestern Europe, in the United Kingdom, in England. They're actually having very big problems with the water quantity at the moment. So it's important to understand the whole history of the climate for your region to be able to better manage your resources. And resources like water, it comes out of the tap, and it's very underestimated the value of that resource, because we just think it's free, it comes out of the tap. We pay a little bit for it, but we think it's free and it comes out of the tap and it's endless, but it isn't. It's probably a better, a more valuable commodity than even oil. Okay, so this is just what it looks like. So you can see this is a very strong El Nino in January, March 1998, and you can see the whole Pacific and then is quite warm. But during a La Nina, a very strong one in particular in 1989, you can see that has abandoned the Eastern Pacific, and now the warm pool of warm water and lots of rainfall is actually hovering over much of Indonesia and the northeast of Australia. These are the ocean temperatures at the same time. You can see the ocean temperature during an El Nino is very high in the Eastern Pacific, and then during a La Nina that is quite cool, and it's a little bit warmer here. But that coolness actually drives the rainfall in our region here. So particularly for Sydney, we were wondering if the ENSO, which is the El Nino Southern Oscillation Cycle that I just discussed, does that drive the rainfall 100%? And if you put them together, so in green it's the rainfall average per year, and then you put the Southern Oscillation, the La Nina El Nino index over the top, then you can actually see that there is a reasonably good fit between the two. So if you then start using the ENSO cycle, the predictive tool in the duration of each of those cycles, then you will be able to maybe predict when that cycle ends. Now, that is statistically a very good tool, but the last few years it hasn't fully fitted 100%, because normally a La Nina period especially on the east coast of Australia doesn't last more than 2 years. But this one has been going on for quite some time now. At the start of the COVID pandemic, started of course in late 2019, that is when our dry period came to an abrupt end in January of 2020, and the La Nina conditions took over. Between August 2019 and January 2020, we had the biggest fires on record in Australia. It burned almost a surface area the size of my mother country, the Netherlands. Some 30,000 square kilometers were burned by natural fires, and it was tragic. Many lives were lost and many properties were lost. Lucky the La Nina cycle took over, and then ever since that early 2000, we had much above average rain. But technically the La Nina cycle was not supposed to last until now, because I think they are predicting it will even go into 2023. So that is almost a 3-year state of La Nina. Normally it slowly moves to neutral conditions, and then it might go into an El Nino state of the environment, which is much drier, but there is a transition period. And even after that 2.5 years, we haven't reached that transition period yet. So this is just an overview of how regional or national a drought can be. So these are just a few examples. So the local drought of 1954 was very disastrous here in the southwest of the country and in the southeast. Same in 1979, patchy record of droughts, but there is, especially on the East Coast here, there was a lack of rainfall, well below average. So that had consequences for the local water availability, so the water quantity. The big El Nino drought, again, with lots of fires that were quite disastrous in Melbourne and parts of on the East Coast near Sydney, that was almost half the continent was in severe drought, because that was the lowest on record almost, and it's half the continent was in drought, and also the most populated area here in the southwest near Perth. So one drought is not unlike the other. So at the moment, we have conditions, as I said, where we have above rainfall. So if we change this to rainfall, then this would be all blue, and then it would also cover almost half the continent. So it is important to state that you have internationally, national scale driven climate droughts, but you also can have local droughts which do not affect the northeast of the country. Now, when we talk about trends in rainfall, this is very important to study in a statistical manner. And then, of course, these are the quadrants of Australia, northwest, which is monsoon driven. It's closest to Java. The northeast, as you can see, it has higher rainfall, but also what is interesting, the amplitude of the rainfall between years is higher than the northwest. And this is a typical monsoon driven system. But it receives rain, as I told earlier, from the east, from the Pacific side, but also from the Indian Ocean side. The northwest only receives rainfall from the Indian Ocean, and the extremes are often driven by tropical cyclones. What is interesting is the trend line. You can see it might be slowly going up. So there is a trend to higher rainfall towards during the 20th century. This seems to be a little bit flatter, and as I said, the amplitude is much larger here. Southwest Australia, low rainfall, only in winter, and if there is a trend here that there are many years of low rainfall, then that will have very big consequences on the major population center of Perth, which is more than 2 million people relying on this winter rain. And if it doesn't happen, the reservoirs go down very quickly. This is the situation for Southeast Australia, where Melbourne is, and Sydney. You can see the amplitude is not as big as in the tropics, but we still have a trend line that goes slightly up. And this is what we experiencing also in the tail end here between 2000 and 2020. In general, the amplitude increased, but that trend line kept creeping up to a slightly higher average. Now, this is we are now flipping to climates of the past, and this is millions of years, and then we go to 10,000 years ago, 1,000 years ago, and then all the way to 2000, 2020. And then we would like to know what we can do with these question marks here in relation to predicting future climate. And as you can see, the climate temperature, global temperature in degrees Celsius has been very high during the age of the dinosaurs, much higher than we're experiencing now. And then during the last million years, there have been big shifts in climates from very cold to very warm. And of course, then the last 10,000 years, we came out of the last ice age, and then it became quite warm, the Holocene maximum about 6,000 years ago. And then we had this is where we, this part of the history of climate is where we have written records, and we also have paintings, especially paintings from Northwestern Europe, where we see a lot of winter paintings with excessive ice and snowfall, called the Little Ice Age. But since the start of the Industrial Revolution, with the start the use of fossil fuels, of course, we are actually on a trend going up again, and then we ended up here warmer than the maximum of 6,000 years ago. And then nowadays we can actually model the climate based on previous observations and a lot of measurement of physical parameters. We can actually start building computer models to see which one of these question marks is closest to what is going to happen in our century and in the next 50 years or so. And that climate modeling is the basis for the International Panel on Climate Change. And I think your president, Widodo, he's behind me, he also signed up at the Paris Accord last year to try and be carbon neutral in 2050, to keep that question mark here on the right at 2050, right in the middle here, at well below 2 degrees, because 2 degrees, we really have difficulties managing our catchments, our drinking water, but also a lot of other resources and coastal management when it comes to sea level rise, which of course goes hand in hand with increasing temperatures. Okay, climate modeling. As I said, the climate modeling really underpins our understanding and what might happen soon. So the next 10, 20, 30, 40 years is really important to know what climate is doing, so we can take action early to avoid massive costs and massive loss of life later on. Now, in the mid-70s, climate modeling and also computer power was such that the model only contained the atmosphere, all the physical parameters of the atmosphere. You can put more CO2 in the atmosphere, and then you can actually predict what's going to happen in 50 or 100 years. Of course, these were not very accurate because, as I said, the computer power was not very large. But then, of course, with the increasing computing power from left to right, you can add more. So in the mid-1980s, they actually put the land surface in, and especially the changes to land surface caused by human activity. We are changing the land surface in a dramatic fashion. And if you leave that out, then your modeling will be quite inaccurate. So in the early 1990s, they also added the ocean and sea ice, because the ocean, don't forget, is about 70% of the whole globe, surface-wise. So that has to be in there. So that was a big improvement. And then you can actually tell that the uncertainties in the modeling forward were actually decreasing. And of course, as you can see, it becomes more and more complex. Around 2000, when I was working with climate modelers, they even included the aerosols, the sulfate ones, which are caused by oceans, the non-sulfate ones, which are caused by traffic and industry, the carbon cycle, so the putting into the atmosphere of CO2, but also taking it out by blue carbon in the coastal zone, or the plantation of forests. That also was taken into consideration in those into those models. And of course, lastly, they put in a dynamic vegetation and atmospheric chemistry. And atmospheric chemistry is also very important because we fully need to understand the physics and the chemistry of the atmosphere, how it actually reacts to that increased CO2. Now, because the the climate modeling became so powerful, even in the early 2000s, you can actually then start doing regional climate modeling. And this is a modeling that was done for my organization at the time, the Sydney Catchment Authority. And these are different sort of the models. Say you can put 550 ppm of CO2 into the atmosphere, or 550, and then you look at what's happening at 2030 or at 2070. And then you can actually see the temperature changes in the different parts of the year. And you can see here under this model in 2070, there are big increases, regional increases in temperature in our state. So Sydney is here on the coast, but the biggest changes are further inland. But that is an area where there's a lot of agriculture depending on irrigation. So this was done. It's still very crude, so there's not much detail in it, but you can actually start saying, well, maybe, 550 ppm, 450 ppm is too much, and this dramatic modeling is actually not very good. And a lot of crops are actually sowed in autumn, and then they grow in winter and harvested in spring. So this scenario will be disastrous. This is the same one, but then for rainfall, it's still very crude, but you can see that there is changes in rainfall patterns between the scenarios. Again, this one here, the winter and spring, there seem to be potential for big increases as well as decreases in rainfall. So depending on which state we flip in, we might actually have a big deficit in spring rainfall or a big surplus. And at the moment, I think we're in this state here already, because we had definitely more than 40% rainfall for this year. But these are long-term trends. So what we can do is we can actually improve the climate model to a catchment size. So these, in the previous one, these boxes, these pixels are quite big. They're about almost like 50 by 100 kilometers. So they're very crude, but you can actually work on trying to make that pixel much smaller, and then you can put in more of the detail of your catchment into your model. And this is where you go from a global climate model. They have pixels of boxes of 200 by 200 kilometers. A regional one has small 35 by 35 grid. And hydrological model that the hydrologists use actually work with a 1 square kilometer model. And what we want to do is the land cover, which is very detailed, put that into the model as well, and then see if we can say more about the specific, still large catchment in Sydney. And this is what happened. This is dynamical downscaling of your modeling. So this is your global model, very big boxes, and this is your regional model, and this is your catchment model. And here you can see the big difference that we expect between 2030 and 2070. There, especially in the mountainous area, the higher elevation, we can actually see there will be increased rainfall, but that doesn't mean that the average rainfall per year might increase, but it's a bit like this year already. The intensity of the rainfall will be much higher, and you will get a lot of rainfall in one event, creating this patchy rainfall. Now, this darkest area is actually just outside our catchment, but the rest of the blue is actually inside the catchment area that fills up the drinking water dam in Sydney. But still, we only have the record of rainfall for Sydney over the last 100 years, 150 years or so, from the records of the meteorologists in Sydney. And this is where the past climate variability studies come in. We can use sediments, but we can also use stalagmites from caves. We were lucky that within the catchment, there is a cave right in the middle, and the cave is an excellent recorder of rainfall that falls on top of the cave, on the surface, throughout hundreds, sometimes thousands of years. And what you want to look for in great detail at very high resolution through this, they grow every year. Depending on the rainfall, they grow fast, or if it's a dry year, they grow very slow, or even stop growing. By looking at all the layers in high resolution, you can, looking at the strontium and calcium ratio, you can reconstruct the rainfall and the droughts. So you can actually go tell if it's a wet or a dry summer or a wet winter. You can actually look at that signal. And we used these caves to reconstruct back thousands of years. And then the last bit, this from 2006 to 1950, we can actually calibrate the older record with the existing rainfall record for that area. So we now have a history of the catchment of the rainfall that goes thousands of years back. And why do we do this? Because this is the past. This is the climate variability. So if we just assume that to the top is wet and to the bottom is dry, so we now know that there has been variability in rainfall from such things as the caves and also from sediments in the catchment. We can actually tell how big the amplitude was and how the duration of each of those cycles, how long it lasted. In the green, we actually know that that is our knowledge band. So if we are staying within that band, we have low environmental risk management opportunities. But if we go flip out of that knowledge band and go into a variation in climate, especially rainfall, then we go into times of highest environmental degradation risk. So what you want to do is, by better management, to increase the knowledge-based green zone, so it covers more of the amplitude, so managers have the tools to better manage and deal with that variability. Of course, the only problem is that we have at the moment that the indications are from the modeling into 2050, 2070, that the amplitudes might actually increase. So at the same time as we increase our knowledge, the amplitudes are increasing. So they are step in step. So we're only catching up at the moment with management-wise of the catchment to deal with these issues into the future. All right. Are we going for time? Is the time okay?
Yeah, the time is now. It's okay.
Oh, yeah, okay. So I briefly want to go into this because not only with the variable rainfall do we have a water quantity issue, but also a water quality issue. So this little study that we did within the lake, the water reservoir for Sydney, which by the way is a World Heritage Area. So it's very precious and it's a beautiful natural environment, but there are some human activities that might actually affect the quality of the water. So this is Sydney, as I said. This is the Blue Mountains area, and here you can see called Warragamba Dam, which is at the end of the lake. And this lake is about 50 kilometers long. And as I said, the catchment goes all the way to south here, to past Goulburn, near our capital of Australia, Canberra, and also to the south here. As I said, it's a World Heritage Area here, the Greater Blue Mountains World Heritage Area, and we actually looked at potential sources of pollution to the lake as a reaction to that drinking water crisis we had in 1998. Now, this is an old photo. This is Tempo Dulu. This is the Tonelli River mouth before damming of the Burgerang Valley. So this is in the 1940s. You can see there is farms and there is grassland for cattle. And then, of course, this is the current situation. These are the same peaks here, as you can see on the photograph. And this is the lake. So this farmhouse and farmlands are all covered by about 20 meters of water. The maximum depth near the dam is 100 meters of water. So it is a really big reservoir. It used to be a beautiful area, but Sydney was already growing much of the 20th century to a much larger population. I think in the last 100 years, we almost tripled in population, something you are familiar with in Indonesia as well. And all these people need safe and enough quantity of drinking water. So that's why they dammed it. And then there is a big lake nowadays. But there are some problems. So this is the remains of a silver mine. They found silver in those mountains near the lake in the 1800s, and they started mining quite quickly, and the silver mine was abandoned in the 1930s because of economic reasons and also its remote location. But the mine site was abandoned, and this is mine waste, and mine waste in contact with water and oxygen can actually produce acid mine drainage, which is the acid that is formed is really good in putting lots of metal pollutants into solution, and it goes down the creek into the major river. But nowadays, of course, it goes into our drinking water lake. So this was a bit of a problem, and we set out to do lots of surface sediment sampling. So here you can see where the crosses are the mine sites. So there was about 4 major ones, and we did superficial sediments, and this is the major creek flowing into the dam here. So this is on the right-hand side where the red dot is. That's where we took a sediment core sample at the bottom of the lake and studied that, but we also took some other samples, water samples, for example, and superficial sediments. So we looked at the concentration of certain metals in water, in sediment, and of course in the sediment core itself, and then had a look at how much was polluting our drinking water. Now this is for the sediment core. We had a 35 centimeter sediment core, and this is using a radioactive isotope with a half-life of 22 years. And we use that to actually date the sediments to see when the pollution started and also when the pollution was much higher than in other periods. So this formed the basis of the sediment study, and this is important to an important dating method of sediments, especially over the last 100 years or so, where you have sediment archives. This is the only reliable method of dating those sediments. So it works a bit like this. Like at the top, you got about 2 dpms per gram. When that decays by radioactive decay to, say, 1.25, that is 22 years. And if that 1.25 decays to 0.6, then you get 40 years, and then half again, you get 60 years. So this decay in value indicates to us that around here is 60 years in the past. Now, this is how you model the age with depth. So this is the sediment core, and this is the age of your sediment. As you can see here, 2 different models. That's not very important today, but you can actually see that the sediments get an age of about 50 years at about 10 centimeter, and then there's bigger uncertainty at the bottom. This is just a better model with smaller uncertainties, but the same thing happens here at about 15 centimeters or so. You have an age of the sediments of about 60 years. Now, what we also looked in the sediment core in the lake was, of course, the grain size, the water content of the core of the sediment, the heavy metal content, especially the ones that indicate potentially from the mine. And you can see zinc, lead, copper, arsenic, silver, and cadmium. They're all, some of them, of course, are strongly related to the silver mines, like silver itself, but also to a certain degree, cadmium and lead. As you can see, there are changes in the heavy metal load, and this is the lead-210 activity on the right-hand side, which we use to create not depth in the sediment cores, but years before present. Again, we compared the concentration of the metals. As you can see here, especially silver, you can see there are changes in silver concentrations in a seesaw fashion. And this is the rainfall from the nearest station. In blue, the annual rainfall, and in red, the 5-year average. We compared it with the grain size to see if the grain size has any effect on it or the organic matter. And of course, there is a little bit of a correlation between some of the metals with grain size and organic matter. But what caught our attention was this, especially silver, the seesaw nature of the curve here. Now, if we look at it statistically, we put the rainfall on the horizontal axis and the silver concentration on the y-axis in this bivariate scattergram, and then you can see that here at the higher rainfall, the concentrations, that's the only trend we could find, is with higher rainfall, the concentrations of silver would be higher. And this is, of course, the distance between the mine sites and the mine waste and the lake is some tens of kilometers through the creek. So only during the wettest of periods with the highest rainfall and the highest flow in the creek that you actually transport precious metals like silver to the lake. And also during those periods, some of the other mine waste goes into the lake and gets buried into the sediments. Now, the problem with the chemistry of some of the other elements is that in the acid produced by the mine waste and going into the creek that leads to lower pH in the creek water, that of course doesn't associate directly with the sediments. But silver, being a precious metal, doesn't have that reactivity with the acid per se, but is more associated with transport by sediments. So this is a direct evidence for us that with high rainfall and high flow into the creek and the transport of the sediments into the lake, we'll actually see elevated levels of silver going into the lake. So we know that was a problem that the mine waste had to be dealt with. So nowadays there are, as a result of our studies, they have actually built retention ponds near the acid mine waste. So any rainfall that washes sediment from the mine waste away is actually detained in ponds, and they can be dealt with. If the pond fills up, it can be actually dealt with in another way rather than going into our precious drinking water. So the last bit I want to discuss with you today is the following. What do you do if there are no sediments or rainfall records for the manager to use? There are catchments where there are no nearby meteorological stations. Sediments are very difficult to find that are suitable to reconstruct your rainfall. And This came about only in the last 15 years, since we have a new equipment. It's called an X-ray fluorescent scanner, and that scanner can actually scan a lot of materials in very high resolution. And this is where we came up with a completely new idea with researchers from the University of Queensland. And we started using tree rings as reconstruction of rainfall. So this is an example of the Acacia cambagii. This is a rather large tree, and this is the dispersion of the tree where it grows. As you can see, Sydney is here. This is the semi-arid to arid region of Australia. And this is where the sample was taken, this sample, right in the middle of the belt of the occurrence in the semi-arid region of that part of Australia. This is the average temperature. You can see it goes up and down with the seasons, and the same with the rainfall. There seems to be a sort of a rainfall peak in winter, but the rest is very low rainfall. So to get a better idea of this rainfall pattern, we started looking in this semi-arid subtropical region at the tree rings, and they don't have very good ring boundaries, which is a bit of a problem. But this is also true for tropical trees in Indonesia. They don't produce rings like they do, as they are traditionally used in the Northern Hemisphere. In North America, in Europe, they can use tree rings in great detail because they have very cold winters where the trees stop growing, and a nice summer season when there is high growth of the tree. And so the tree rings are very distinct and easy to recognize. So here in the tropics and in the full tropics like Indonesia, Thailand, Vietnam, where we also have done studies on tree rings, there are no tree rings to speak with, because temperature-wise, the temperature is quite stable over the year. The only thing that might differ is the availability of rain. So there's indistinct ring boundaries for this species, no clear alternating bands of early wood and late wood. And so standard dendrochronology methods you cannot apply. So this is the machine that we use. This is the Artrex core scanner, which we purchased 10 years ago now. And this is one of the most powerful machines that we have in Australia for the study of not only sediments, but also wood samples. And we can also analyze the stalagmites from caves, and in extreme detail. The highest resolution that we can apply to this machine is 250 micron per analysis. So that is 4 points of analysis per millimeter. And you can imagine if you have half a meter of tree ring or a piece of wood, half a meter long, that is a lot of measurements if you do it at 250 micron interval. And what the scanner does is in sequence. So it first takes a beautiful picture, high resolution line photography, and it stitches together to a very high resolution optical image. That optical image is followed by an X-radiograph. So you can actually look into your sample, like having an X-ray at the hospital when you see if one of your bones is broken. This machine can actually look into your sediment, into your stalagmite, or into your piece of wood and see if by X-ray there is actually tree rings visible that are not visible in an optical image. After that, the machine resets itself, and then it starts the XRF, process. For XRF, we have to prepare the wood in a special way. We make a very thin wafer of the wood, about 1 or 2 centimeters wide, and maybe 3 millimeters thick. And that wafer of the timber made by this special machine goes into the machine, and then every 250 micron, the X-ray source will beam the X-rays onto your sample, and it causes all major elements, chemical elements, to give off a fluorescent signal with a specific energy for that element. And then within 10 seconds or so for that measurement, it will move to the next point, 250 micron down your record. And every time it does that, in that 10 seconds, you get a profile or a concentration of about 30 chemical elements. And that's the important bit. And it looks a bit like this. So at the top, you can see the optical image, which was done at 200 micron. The X-ray scan, we can actually do very finer resolution at 100 micron. And you can actually see the difference between the two. Yes, you can see details in the optical image, which you can see some tree rings and different colors. But especially in this light bit here, there's not much to see. But if you look at the X-ray scan, there is actually an enormous wealth of data available, and the resolution of the fine resolution of these layers are now visible to us. And combine that with the XRF, the fluorescent signal from the same samples, you actually get, we use strontium and calcium as an example for this tree, for the Acacia cambodgii. As you can see, the resolution is somewhere in between the optical and the X-ray scan, but you can see there is big differences throughout time in the concentration of strontium and calcium. Now, what does a tree do? A tree needs calcium, and strontium is chemically very similar, or almost identical. They take it up when there is lots of water available. From the groundwater, from the soil around the roots. And not many people know this, but in Canada, they produce maple syrup, which you can use on your pancake. But if you look on the label of maple syrup from Canada, you will actually see it's very high in calcium. It's almost like drinking milk. So we know that trees are very good in calcium uptake, even in the structure of the tree rings. So that is a very good indicator to us for water availability around the root system. So in wet periods, there's lots of calcium, and in low periods, dry periods, there's less calcium available from the water. Now, as you can see here, the years 2012, 2002, 1969, 1963. Now, these were important ones to calibrate this data set with the closest meteorological observation station, which was not very close by. It was quite a distance, but we needed to calibrate these amplitudes of the strontium and calcium with the current rainfall, and we did that. So first of all, these 1969 and 1963, we actually analyzed the tree rings. We took a tiny sample here, and we used accelerated mass spectrometry, radiocarbon dating, to date those tree rings here as pieces of wood. And they form part of this curve. This curve started in the 1950s, and you can see it's deteriorating over time. And these two have to be on that curve, because what happened in the 1950s, the superpowers like America, Russia, and also China started experimenting with nuclear bombs. And of course, the nuclear bombs in the atmosphere, they produce lots of radiation, and that actually produces from nitrogen a lot of carbon-14, which is radioactive. And you can actually measure that in lots of tree rings, but it has been measured in the atmosphere. So the concentration of radiocarbon in any tree ring has to fall on that curve. So the two separation by about 20 millimeters or so, they have to be both on the curve. So we put that on the so the blue ring is what we base on counting the rings back from 2012, and the dark one is actually based on the measurement of that concentration of radiocarbon. You can see they fall on the same place. So this is a very high reliable dating method to calibrate these, not the millimeters, but then it becomes calendar years. And this was important because then you can actually calibrate your strontium and calcium set with your rainfall record. And this is what we did here. So we have the stable isotope record here, and then we know all the years from counting down, and then you can actually see if there is a strong correlation between the two. And that is what we came up with for this is the rain index, and then we have the cellulose and stable isotope index. And then we actually came up with a really good correlation, a reasonably good correlation for between the tree ring and the calcium and strontium, and also the other isotopic information we get from those tree rings for rainfall. And we can actually say with a reasonable amount of confidence that if we take another tree and we do the rainfall, we do the tree ring analysis with the XRF, which only takes maybe 1 hour to do. It's a very rapid method. Then we have another rainfall record for another area which might not be close to this one, but because we calibrated this one, we now have millions of potential rainfall stations by looking at tree rings. So if your catchment does not have a sedimentary or a cave with a stalagmite or a good written record of the climate, you can actually use suitable trees to reconstruct rainfall back in time using the tree rings. And this was quite new. It was published straight away in the Journal of Arid Environment. And this gives managers of catchments in regions where there are very bad records of past climate, a tool that they can use in looking at past rainfall events and future trends. So again, by that new tool, we have increased that green zone here where we can actually deal with the current amplitudes, but also if the future amplitude might change, hopefully it all falls within that green band by putting extra tools into the boxes of the managers of catchments. And I think this is a very important thing that scientists at government institutes or universities, we really all have to talk to the managers of water resources and try to help them as much as possible, because we all depend on not only water quantity, but also water quality. And we can only learn from the past to better manage the future. And I think that is the last slide. So terima kasih, and hopefully you found it interesting. And I'm happy to answer lots of questions. Thank you very much.
Thank you very much, Professor Hein, for the presentation. And before we start with the discussions, I would like to invite to the audience who would like to give some questions or perhaps some comments about the Professor Heng's presentations? Is there any? Okay, so we can wait. So meantime, then I would like to ask some questions, Professor. I'm interested with your presentation, student presentation. It's quite new for me, but yeah, my background is physics also, radiation physics. So I can follow your idea about using another X-ray and also the HRF analysis to do, I mean, to make a local stations to do the what is it, the modeling for the climates. It's interesting for me because the idea is to use the tree as a plot, as a potential area or sample area to do the scan and to understand whether on that location, on that specific locations, we can see the trend of the climate, especially with the water resource. And then when we can do many samples, then we can have a wider coverage area. Then we can have more maybe in the sense that more accurate variability. It's really interesting for the idea. But maybe in your earlier presentations, I really would like to know about the climate itself, because from what I saw like cycles in the climate. So sometimes the water condition is going up, and then sometimes it's going down and going up again and going down again. So it's like a cycle. And then based from your presentations, the cycles runs like in 100 years. So can we say that the cycles is a normal conditions? That means in the future, this kind of cycles is also will be do the same, or will it goes up without going down due to the climate change that is happening right now, like the warming of the earth? So perhaps you have some idea of that or some comments on that.
Oh, thank you very much. That is a very good question, and I think yes, there are cycles, and that's what we need to deal with. And the problem is these are natural cycles. And it's only the last few hundred years that humans have had an impact on those cycles. So the human influence is on top of the natural cycles. So when I did my PhD research, I was looking into the ice ages and how long so during my PhD, I was looking into the ice ages, and these are climate cycles over tens of thousands of years. And my interest was in the warm periods that are in between ice ages, and the temperature difference between a full ice age, where most of North America and Northern Europe is covered by glaciers and snow and ice, and a warm period is only about 3 or 4 degrees annual temperature. So there is only the few degrees difference makes a big difference in the local climate in the Northern Hemisphere. So the duration of an ice age is much longer than a warm period that are in between. And that model was theoretical model was thought up maybe 80 years ago, but only the last 50 years ago, we actually can, or the last 25, 30 years, we can, in high resolution modeling, we can actually test that model to see if that's correct. Now, that model tells us that the current warm period that we live in that cycle, on that 10,000 year cycle, that a warm period will last, will come to an end. We will go into a next ice age. But of course, of the industrial revolution happening and us pumping extra CO2 into the atmosphere, we're actually changing that natural cycle. The trend would have been to colder conditions, but because we're actually warming up the Earth by putting these greenhouse gases into the atmosphere, we're actually overriding that natural signal. And that is the global long-term cycle. And then, of course, we have shorter-term cycles, such as I talked about, the El Nino-La Nina cycle, which is a natural cycle because we can study that in corals, and we know that that cycle has been going on for thousands of years. And there have been periods extensive periods where the El Nino was longer than the La Nina and vice versa. And it keeps going. And of course, we learned from that, but what we don't know, but the computing models are now so powerful that even the variation in the La Nina El Nino cycle can be incorporated into that global climate model. And we can actually see if the increase in CO2 will have an effect on that cycle. And it is not clear yet what the direct effect will be, because as I said, that cycle is so short, like 2 to 3 years. That is very difficult to predict. But what climate modelers do is they use the observations, say, from 1900 to 2000 as input into their model, and then try and predict the short-term climate or even the weather on a seasonal scale into the future. And that is where the computing power comes in. So what they did was they can actually sort of predict, not with a high reliability yet, but they can use the previous 100 years of meteorological data to test their model to see if they can predict what's going to happen next year. And I think we were warned in Australia that the winter rainfall especially would be more intense and we would have floods. And everybody was laughing, especially in the right-wing media that don't believe in climate change, that they said, oh, that's nonsense. They don't know what they're talking about. We are in a drought now. It's not going to rain that much. But now it's happening. And their predictions were reasonably accurate. I mean, they cannot tell which week it's going to rain in, but especially the fact that they predicted higher intensity rainfall in winter, which is unusual for Sydney, because one of my slides said we have uniform rain throughout the year based on 100 years prior. So yes, there are cycles, and we are tinkering with it, with the increased CO2 in the atmosphere. We don't know all the answers yet. A lot of people say, oh, we know that climate change is happening. We don't have to do research. One of our previous governments said that. That is a very dangerous statement to make, because we don't know, we don't fully understand the system yet. Yes, we understand a lot more, but it's a bit like looking at other fields of study, like medicine. You don't say if you can cure one cancer that understand all cancers and then don't have to put more research in. You want to fully understand all the mechanisms, and this to a natural system, it's the same thing. So we are not finished yet, but we can say with a lot more confidence what is going to happen to our climate. The biggest criticism of the International Panel of Climate Change in the 1990s and early 2000s was that they could not give certainty or uncertainty to their predictions. And in the last two reports since 2010, they worked really hard on that, the world community, to say with better precision and certainty what the predictions are going to be, or what the predictions are and what the consequences are going to be. Okay, hopefully that answered your question, but
Yes.
it's really a matter of trying to add as much data to the database.
Yes, Professor. Based on your answer, it's also drive me to another hypothesis that well, you said that perhaps due to the global warming, it shifts the natural cycles to another levels. So is it safe to say that so we will have a different baseline? So for example, well, if we can say in the terms of degrees Celsius, perhaps. If the normal temperatures will be very, for example, in the tropical area, between between 20 until 30 degrees, for example, it will fluctuate between 20 until 30 degrees. And due to the global warming, then the average temperature will rise until 28 degrees. Then the cycle will be vary between 25 until 35 degrees.
Yeah.
Is that kind of cycles that we will experience in the future? So we will have like upgrade baselines of temperature variations in this case, for example. Do you have any comments on that?
Yeah. Well, the interesting thing with the tropics is that the impact in temperature will not be as great as the rest of the world, because the tropics are in a sweet zone. Well, they're right in the middle. So the seasonality of the sun warming up the earth is rather constant in the tropics. That's why it's a tropical system. When we talk about 2 degrees warming globally, that is globally. And for the tropics, it might be 0.5 degrees, which is not a lot. But in the high latitude of, say, the Northern Hemisphere, and also in Antarctica, where there is big seasonality, there a 2 degree is probably more than 2 degrees. What we're currently seeing in Greenland, which is the storage of a lot of fresh water by means of snow and ice, they far exceeded the temperature increase of what we have at the moment, which is 1.5 degrees globally. They're looking at 5-6 degrees temperature increase already. Because what happens is the Northern Hemisphere land surface changes in color. Maybe 50 years ago, snowfall in winter and the winter season lasted longer. The land surface was white. White is really good in reflecting sunlight back into the atmosphere. So it actually doesn't warm up the soil. By increasing the temperature, and that actually, the snow cover will be less and less and less in duration during the year. So most of the year, the land surface will be either green or brown, which absorbs a lot of warmth, a lot of heat. And of course, that accelerates the process of melting ice. Yeah. And so you might argue that it's not as important for the tropics, but because all that meltwater will lead to rising sea levels. Yeah. And of course, that is a worldwide problem. So 2 degrees global warming is, lots of people argue, yes, but for me in Jakarta or in Sydney, we won't have 2 degrees, we have 1.5 degrees. But people in northern Russia, they have to deal with 4 or 5 or 6, 7 degrees, plus also a very changed landscape. And don't forget that a lot of the carbon storage in the swampy areas of northern Canada, the northern Russia, they contain a lot of buried carbon, and they have been buried in permanently frozen soil, covered by snow, not warming up. And that is starting to melt now. And that accelerates the release of not only CO2, but also methane, which is another greenhouse gas. So once that's starting, it's actually a flipping point. There's a point of no return where you can actually not stop it by saying we stop all CO2 going into the atmosphere. And the risk is that it's going to be a runaway process that will drive regional temperatures to go up very high. And the risk of the other areas that won't see an increase in temperature will be the increase in sea level. And I was on fieldwork yesterday near Semarang here and looking at mangrove systems. And you can already see that the minimal effect of, maybe 1 or 2 centimeters of sea level rise has an effect on the mangrove systems and people's livelihood in shrimp farming, fish farming, and even rice paddies by coastal inundation. So it's still, we have to be very careful. We're actually playing with something we cannot control. I think it's too late for control. We now have to prepare ourselves for how we're going to handle the new situation.
Yeah, okay. So it also leads me to another questions, because how can we, so to which directions do we need to do our research in the futures? So, should we should we focus on manipulating the climate or the weather? So, for example, like making a local rain methods, for example, by using the plane and then sending so many salts to make rain in some area, or do we need to manipulate the weathers, or do we need to focus on fixing the problems, the environmental problem due to the weather changing? So, which directions effectively can we do research, or can we focus on doing things in the future?
Yeah, that's a very good question. I think the trying to influence the weather, and especially say rainfall, we have experimented with that in the past in Australia, but during the dry periods, the problem is you cannot use cloud seeding to produce rain, because the dry seasons don't have clouds.
Yeah.
You have dry periods and it's blue sky. Because there's no condensation of water in the upper atmosphere. So that didn't work for us. I think what we really need to do is to prepare ourselves for producing energy that does not use fossil fuel. Because if we stop us using it, and we will be carbon neutral by 2050, which most governments have signed on to, then at least we have a chance that the changes are not that large that we greatly endanger the world population in a socio-economic way. The Earth will survive. I mean, I showed that there's big changes in climate over the times of millions of years. Yeah. But we as humans are very uncomfortable with change. We like the status quo, and so for us, we have to wean ourselves very quickly off fossil fuels and find alternative sources of energy, because to deal with the changes that are coming with the current concentrations of CO2, that will cost a lot of energy, but it can't be fossil energy to deal with it. Coastal defense works, like with lots of concrete and beton to build protective walls, build a new capital for Indonesia in Kalimantan. Mm-hmm. That all costs a lot of energy. Yeah. But traditionally, that energy comes from fossil fuel. And so we should not fall into the trap trying to fix a problem by making it
another problem.
Trying to solve it. So we really need to look at alternative sources of energy. And of course, in Australia, we are looking at solar energy, geothermal, wind energy. And I also think that at some stage they will have to look at nuclear energy. which is very, it can produce lots of energy from minimal amounts of resources. So, and Indonesia is looking at very similar options. I think geothermal is a very good option for Indonesia in large population areas like Surabaya or Jakarta, Makassar. The use of smaller nuclear power stations is a very distinct possibility. It's just that, yeah, we don't want to make the situation worse. When I talked about the amplitude of problems and the green zone, we don't want to increase the amplitudes by putting more fossil fuel into the system and then forget to work on the green zone. We really want to reduce that amplitude and massively grow that green zone, how we can manage with those changes.
Yeah. Okay. So one last question, Professor.
Because
I really interested with your climate models. So in the beginning, the climate model only include the atmospheric conditions, and then by time it's also include many parameters to the calculations. So my question is that which parameter gives the main predictions to the models? I mean, do they share the same? Do they share the same percentage? The percentage, I mean, or is there any key parameters that we need to take into account more than the other parameters? So the primary and secondary parameters, for instance. Maybe you have some idea for that.
Yeah. Well, when it comes to those models, the main parameter that drives the change in future predictions is, of course, CO2. But we know that CO2 is not the only greenhouse gas, because we also have methane. So they realized that methane was pretty understudied and also underrepresented in the models. So the last 10 years or so, they are really working hard on methane budgets, the methane cycle, to improve the model. The model it's still not 100% accurate. And when I talk about the model, there is no such thing. There are many models, and there are a few that are dominating, but every few years there's an inter-model comparison run by the World Meteorological Organization, and they compare the models with each other to see if they're actually predicting the same change within certain uncertainty. If your model is not within that uncertainty, then there is something wrong with your model, and then you have to work hard for the next exercise to be within the successful models. Because the World Meteorological Organization is very strict in this, because some models predict that they vastly underestimate the effects, and other models might vastly overestimate the effects of increased CO2 and methane, and they can actually lead to unrest and governments making the wrong decisions. So the World Meteorological Organization has a very strict protocol on testing these. Now, when it comes to methane and also CO2, the budget of calculating the budget of how much is put into the atmosphere, released, and how much is buried, it's very different for CO2 and for methane. So only recently they started using high-resolution satellite measurements of methane to get a better grip on the sources of methane in the atmosphere. And it is very interesting. It is only the last 2 weeks that they found out that there is massive sources of methane from the largest rubbish tips in the world. So in India, there is a massive rubbish tip near Mumbai, and that is a very big point source for methane. And if, for example, if you don't fix that, and there's tens of these massive rubbish dumps around the world producing lots of methane, and rather than harvesting it and using it, it goes into the atmosphere and causes probably the process of warming to accelerate rather than trying to fix it and bury it. So the models, as I said, they found out that CO2 was not the only answer to the rate of warming. So there were other components that they were underestimating or didn't know about.
Okay.
Yeah.
So, I mean, in the end, it's about human activities.
Yeah.
Yeah. I mean, the one that we consider, or the main resource of, like, for example, the main resource for the productivity, human productivity, like is it the solar, and also the coal, that to do the industrial working.
Yeah.
But in excess, it also produces CO2 that also can raise the climate, the global temperatures. But as you said, there's also another factors that perhaps not many of us know about it, that also can change the climate change. The climate temperature, also the climate change. It's quite interesting presentation, Professor Hein, and also it gives us so many insight that many things. I mean, what human do in life will give effects to the environment, and then what the environments when the environment change, it also give feedback or impact back again to the human. So it's like it's also another cycle. how we live in this world.
Yeah.
So, yeah, it's quite interesting. And thank you very much, Professor Heijnis, for sharing the knowledge with us.
Yeah.
And then we hope that we can also continue our discussions after the class return to the luring to the offline class, perhaps, so we can have like fruitful discussions.
Yep.
Or then the online presentations.
Yep.
And to close the presentations, we would like to give our appreciations to Professor Feng for your presentations. We would like to give you the certificate from the Dean for your attendance as the visiting lecturer to today's presentations. So please receive this certificate. We will give you also by hand. And then before we close the sessions, we would like to also we would like to also be thankful for all the participants who already joined the lecture until the end of the sessions. And also to Prof. Manning, who already accompanied Professor Hank during the sessions. And without further ado, because the time is already up, it's 11 past 10. So we will close this visiting lecture presentations, and we would like to give our time back to the Mbak Ali. Please, the time is yours.
Okay.
Thank you, Pak Panji. Thank you very much for Professor Hendrik Heijnis from Australia and Pak Panji as a moderator for today visiting lecture. Okay, next, please all the participants kindly open the camera. We would like to invite to taking virtual group photo. Mas Oki, please kindly to lead the taking virtual group photo. Okay, thank you. Excellencies, distinguished guests, and ladies and gentlemen, we have had productive and inspiring time together, and this event about to come to the very end. I hope you have found the presentation of this visiting lecture are informative and helpful. Thank you, and see you in the next session.
Okay, thank you. Thank you very much, Prof.
Thank you.
Okay. Mas Sofi, this is already you take a photo?
Bagaimana, Bu?
Sudah selesai fotonya?
Sampun, Bu.
Oke. Oke, thank you.
Yeah.